Okay. I officially lived through my fishing trip. It was awfully cold on Lake Superior, though. It was really cold. Um, how did Friday go? So I know I tried covering the notes for both Thursday and Friday on Thursday. Did Friday seem to go okay, or is there things you guys want me to work on with you first? Because I could certainly answer questions before we start today's information. All right. If you do have questions from it, obviously just ask however you want. You can ask in class during these live times. Once I'm done teaching, when we have kind of the whatever time left over at the end of the hour, you can ask me questions then to work on with you. From 1:35 to 2:15 every day, or I shouldn't say every day, I should say Monday through Thursday, I am always going to be on just open Google Meet office hours. So if you guys have questions, it's basically like 45 minutes after third hour's done. And you can always just send me a message. I mean, a lot of you have been taking advantage of that. Certainly, however you feel comfortable asking questions, feel free to do it. So the three things we need to cover today are classifying discontinuities and then trying to state continuity at a point. And then that's from both a graph and from an equation. So let me at least talk about discontinuities before we even worry about them. So there are two types of discontinuities. There is what's called a removable discontinuity. And the spelling in this section is always horrible. You got to spell real slow. And then there is a non-removable discontinuity. So, and if you're not sure what discontinuity is, basically, if your function or graph isn't continuous at any location, that would be referred to as a discontinuity because it's discontinuous. So the reason they classify them differently is it's kind of almost like thinking like how severe of a discontinuity it is. So a removable discontinuity is when a single point is removed to create a discontinuity. Now that can be done multiple ways. By far the most common or the easiest example would be a hole. Who should we go with? Should we go with David? David, do you think you can help me out? Yes? Okay, excellent. Excellent. Okay. Do you remember how you would identify a hole from an equation? This is kind of a tough question, so don't feel horribly bad if you don't remember it off the top of your head. Yeah, whoever whispered that, yes. Yeah. So a good example of that is when you have a factor that cancels. So, oh God, what am I writing? So it only happens if you have a factor that cancels. So like this example, x minus 1 would cancel, and then that would leave a hole at x equals positive 1. And then that would be a removable discontinuity at x equals 1. Now, there are definitely other ways to make that situation happen. So if you think of a piece function, you could have a piece function that has two pieces. And if those two pieces come together and meet up, but yet these two pieces don't have right on that value, well, then those two pieces are on each side of the value, and it would create a hole in between them. So that's another way that you could have a removable discontinuity. I will basically tell you that 99% of the removable discontinuities are from a hole. And so that's why I put that example up there. That's by far the most common way to get that one. But there are other ways. A non-removable discontinuity is sometimes called a jump or a gap discontinuity. So the AP test and the AP exam and Khan Academy sometimes refer to them as jumps or gaps. And that's because these discontinuities essentially mean that there is space between the pieces. Okay? It can happen a lot of ways. A common example would be a vertical asymptote. So a vertical asymptote automatically creates space between pieces. You know what, David, I'll let you call on the next person since you had to suffer through the first question. First question's always the worst. Jack? Okay. Yes, that's how you identify it. So a vertical asymptote is when you have a factor in the denominator that does not cancel out. So like this example, if I write x plus 5 in the denominator, then this would be a vertical asymptote at x equals negative 5. So factors are generally how you identify holes and asymptotes. And basically, if it cancels out, it's a hole. If it remains on the denominator, it's a vertical asymptote. But that, by far, is not the only way to get a jump or a gap in a graph. That's just a common one. Okay, these are the only two types. So if I ask you to identify any discontinuities in a function, you're going to choose between those two. And by far the easiest one to identify is a removable, because it's a single point that's removed. So it'll look like a hole no matter how it's created. So these are discontinuities. Let's see, maybe I should just write some equations and have you guys see if you can identify a discontinuity just from a function, not from a picture. From a picture is generally a lot easier. And so, I mean, like a lot of you can just look at a picture and say, well, right there, it's not continuous, you know. Let me put up some equations. And so David and Jack, you guys are good to go. You've already answered. You're done for the day. Now we have, 14 other people to pick from? So identify any discontinuities. Discontinuities. I hate this. The word is so hard for me to spell. Okay, so let's see. I wrote some equations down so we could pick some. So let's go with the first one. will be f of x equals 1 over x squared minus 4. The second one, g of x, would be x squared minus 1 over x plus 1. Third one, fg h of x, would be 1/2 round down, or greatest integer function. It's so hard to write that symbol. I'm running out of space. And our fourth example will be a piece function. Ugh. Let's make that symbol better. We'll go with it. X, when x is less than 1, 2, when x equals 1, and 2x minus 1, hopefully this comes out, x is greater than 1. Okay, we will take some time to talk about these two. So it's not like I'm expecting you guys just to look at it and be able to, answer it off the top of your head. Okay, Jack, is there somebody you want to call on? Caden, okay. Wait, which Caden? Because isn't there two of them in this class? Okay. Okay, Caden, I'll give you the choice here. Any one of these four. Are there any discontinuities, and where are they? And okay. I can't hear you. There's some sort of weird cycling noise. Yep. Perfect. Okay. So the first one has two discontinuities. Which, I mean, it's not like you have to answer it like this. But it's going to have two discontinuities. You're going to have, both of them are non-removable because they're both vertical asymptotes. So we have, if you want to just abbreviate it as NR, go for it. I'm going to write it all out just for the notes. Non-removable discontinuity at x equals positive 2, and a non-removable at negative 2. And then Caden, at the end of class, before I forget, I need to talk to you about Khan Academy. Okay, nice job. So let's go with who we called on for a while. Oh, Mackenzie. Mackenzie hasn't answered because she didn't have a Chromebook to answer. Hers wasn't working. I know. So I suppose from now on you're just going to pretend it's not working, huh? It's where I can hear you. Yeah. Okay. So, out of the three remaining ones, is there one you feel more comfortable working with, or looking at, or talking about? Okay. Okay. Nice. Nice. Perfect. Absolutely perfect. So this one has a hole at x equals -1. So this would be a removable discontinuity. Good job. Okay, so those are kind of two straightforward ones. And honestly, you see those the most. So that's why I wanted to make sure that those are part of it. C and D. Oh, go ahead. Yeah, go ahead. -1. Because there's going to be a hole at -1, because if I put -1 in place of x, then that would make it undefined. So generally, it's whenever you set the factor equal to 0. Okay, so you probably, I think we went over this symbol on Thursday. Maybe it was last Wednesday. This symbol, if you see a double bracket, is the round down function. It's got 3 names. Okay. In your calculator, it's called the greatest integer. It's also known as the round down function. It's also known as the step function. So, I mean, the name of it isn't that important. It's basically that you know that those double brackets means the graph is going to look like this. Okay? And honestly, the rest of the details just determine what the step looks like. Like if I remember correctly, this graph, the steps are actually angled. But we don't really care about that. What we care about is it's going to have steps. So if I'm talking about discontinuities, I need to get a color. If I'm talking about discontinuities, well, there's going to be a discontinuity every time there's a step. So this one is going to have non-removable at every integer. Now, I don't know how well you remember transformations in pre-calc. You have to look at horizontal transformations. Where's pink? If that was a 3x, okay? 3x, if you remember on horizontal transformations, 3x made everything happen 3 times as fast. Like if you think of trig periods, 3x made it the period 3 times as fast. So on a horizontal transformation of 3x shrinks it in by 3. So what would happen is you would have a step every 1/3 integer. So like each one of these steps would be shrunk by 3. So you're going to have to do horizontal transformations to kind of identify how often the discontinuities happen. And these are unfortunately a lot of the details that you're just supposed to kind of remember, because that was the whole point of learning them in the previous years. So I guess my point is, if you run into a strange one like this, the double bracket should tell you in your head that it's going to be steps. Okay, so I know there's non-removable discontinuities. To determine how often that happens, you have to look at the multiplier on the inside. Because the multiplier on the inside is opposite, because that's what a horizontal transformation does. If this was 1/3 x, then your step would be 3 times longer, and it would happen every 3 integers. Go ahead, Caden. Inside. No, I mean, you're asking a good question. I'm thinking. Because a multiplier on the outside technically is supposed to stand for vertical change. A multiplier on the inside is supposed to stand for horizontal. No, it would just be inside the parentheses. You're not going to get one that complicated that we'll have to worry about the difference, I guess. I'll put it that way. I just wanted to write that little note so you guys would know to look for things like that. But yeah, no, that was a good question, because a 1/2 on the outside kind of is like a 1/2 on the inside. But on the round down function, it's not actually the same thing. Okay, let's look at the last one, though. I was wondering how well you guys remembered piece functions, and that's why I chose that example to try. Do you guys want me to go through and graph that piece function with you? Okay, I certainly can. That's why I said I didn't know how well you remembered it. So I can graph this with you. So let me make a little axis here. So you technically don't have to graph a piece function, but I think a lot of you are probably more familiar with that just because that's how you do it in your head. So we are going to have y equals x. Maybe I'll try to do this in colors. Y equals x to the left of x equals 1. So 1, 2, 3. So instead of me having y equals x be the entire graph, we are only going to have this graph to the left of x equals 1. So whether I do this as a mental dotted line, I can physically write it in, doesn't matter. So y equals x, it's going to be a hole there because it's not equal to 1. But I'm going to graph to the left like that, I guess. And then it's going to be y equals 2 only at x equals 1. So that's the point 1, 2. So y equals 2 at x equals 1 only is the point 1, 2. So we are going to have a solid point at 1, 2. And then we're going to graph 2x minus 1 to the right of 1. So at x equals 1, it would be 2 minus 1 or 1. It would also be a hole right here, so it's a hole right on top of the other hole. And I'm going to have a slope of 2. So up 2 to the right 1. So it's just going to be like a steeper line. Okay, so this is a weird looking piece function. But I have a feeling a lot of you would like to sketch piece functions because it's hard for you to visualize them in your head. And there's nothing wrong with that. You absolutely can always do that. Now, before I move on though, does somebody want me to explain why I graphed one of the pieces like I did? Or how I knew to graph it, wherever. I mean, like, ask away any kind of questions on that graph. Because you have to be able to do it on your own. Okay. Then KR. Who the heck is KR? Is that what you go by? No. Okay, got it. Okay, so Caitlin, can you help me out here? Do I have any discontinuities? Perfect. I have a hole at 1, 1. Now, I actually don't even have to give the point. So there's nothing wrong with just saying I have a I have a removable discontinuity at x equals 1. So they usually just want the x value, not even the point. But since that was happened, there was a single point that was removed in between those two lines. So that's a removable discontinuity. This point actually means nothing in terms of discontinuities. This individual single point actually means nothing in terms of individual discontinuities. Okay, now here's the other half of the, what are you going to call it? We identified discontinuities. Sometimes you are going to be asked to identify where it is continuous. So, Caitlin, can you pick somebody else for me? Is this like the worst part ever? Oh, okay. Sounds good. Julia. Okay, I'll just pick a random one up here. Let's go with A. If I asked you to state where this function was continuous, what would you say? I can write it underneath if you want. Perfect. Not just between, but basically everywhere but at the asymptotes. Yes, no, that's perfect. Isabella, yes, your question I saw it pop up there. That point doesn't even need to be there. It's still going to be called removable discontinuity without that blue point. It would still be called that. So A, if you had to say where A was continuous, we would say it is continuous, and we usually use interval notation. So we would say it's continuous from negative infinity up to negative 2, along with negative 2 to 2, along with 2 to infinity. You don't have to use interval notation. You could use inequality notation. So you could say like x is less than 2, or negative 2 is less than or equal to x is less, or negative 2 is less than x is less than 2, or x is greater than 2. Most people just like inequality notation because it's cleaner. So it is possible. So why is the step function non-removable if it's only at a single point? So the step function is called non-removable because you have an actual space or a gap between the pieces. I don't know if that's the best way to say it. It's only called a non-removable if you have a single point empty and a line before and after. It actually doesn't even matter if the lines are the same angle or not. It's only going to be called removable if it's a single point that is missing. So like if you have two lines, like the pink ones from the step function, there's an actual gap or a space here. So this is not a single point removed. It's a single x value, but not a single point. I think that's maybe the difference that you were getting stuck on. Okay, I don't know. Any other kind of questions from that? What's up on the screen right now? Because that's a lot of information. And for time-wise, I'm gonna skip the next. I was gonna put some examples up and have you guys say where a function was continuous, but I think I'll skip that for now, just because it's honestly it's not really any different than what we were doing right here. You just say the other half of the answers. But we still have continuity at a point to talk about. And I don't want to, like I said, my goal is to try to use up no more than an hour each day for trying to do work together if I can, because otherwise it's hard for your brain to absorb that information past that point. Just wait till you get to college and they have 4-hour classes. Those are ridiculous. It is so hard to focus for 4 hours in a row. So continuity at a point. We'll go with a graph to start with. So let's go with this graph. Oh, that green is actually hard to look at next to yellow. Let's go with pink. Sure. Oh, that makes it really hard to... There. We'll just make that 1.5 instead, make it easier. Okay, I have no idea what graph this is. I'm just kind of winging it and making it up. You would be asked if the function is continuous at a point. So when they say point, they actually mean an x value, and they don't actually mean a point. So I don't know why they usually phrase it as continuity at a point, but it actually means an x value. And it's kind of strange for me because calc is usually really particular about wording. Okay, so is this continuous? I'll just call it f of x. At x equals 1.5. Now, from a graph, I'm going to guess this is probably a lot easier to figure out than from an equation. We should go with Lila. Lila, is this graph continuous at x equals 1.5? That definitely sounds like a guess. That definitely sounds like a guess. Okay. So, what part of it is like, are you stuck on or iffy about? Is it this? Is it the point up here or the hole down here? Perfect. You can draw it without lifting up your pencil. So no. Correct. Correct. Nope. The questions aren't always supposed to be tricky. Now, some people have a hard time looking at the picture and identifying holes. So, I don't know if you were just flat out overthinking that one. It is also possible that you're going to get asked this same question. Okay, so is f of x continuous at x equals 2? And Lucas, is it continuous at x equals 2? Ah, perfect. Okay. So I wrote 2 because something tells me this is the number they would give on the AP test. And the only reason I even wrote 2 is because this point is up at a height of 2. And so I'm wondering if that's what you went from, Lucas. The answer would be yes. Because at x equals 2, right here, it's just part of a normal line. The limit from the left, the limit from the right, and the function value are all the same. That's technically what you're supposed to look for when you're trying to identify if it's continuous at a value. So can I shrink this stuff? Oh, look at that. So I will write it for both of them. Get out of the way. There we go. For the first question we went over, I would technically want to find the limit of the function to the left. I would want to find the function value. And then I would like to find the limit of the function to the right. So this is the actual way to prove it if you need to. And the reason I'm bringing it up now is because this is what we have to do when we have an equation and no picture. So the picture, you can kind of just look at it and try to figure it out. But so the limit to the left of 1.5, so to the left of the whole, is going to be at a height of 0. The limit to the right of the whole is going to a height of 0. And I wonder if I can zoom in far enough to... Whoops. If I'm looking to the left of x equals 1.5, I can see that it's going down to a height of 0. If I look from the right towards 1.5, it's going to a height of 0. F of 1.5 means I look directly above 1.5, and this is f of 1.5. So f of 1.5, f of 1.5 would be 2, because there's a point up at y equals 2. So the fact that all three of these are not the same would mean it's not continuous. That's what has to happen for it to be continuous. Now the third one, or this next one, I don't even know what the height would be at this one because I didn't pick a number that worked well. But this second one, you can see it's continuous because it's on a regular line.
Finished. Well, I put away all my clothes with one song.
Oh, nice.
There wasn't that many clothes.
Oh.
The reason why.
Okay, let me put up an equation. So we'll go from one with no picture. So this is continuity at point analytical. This would be probably where we might end up. We'll see. I can maybe make up another one. So is f of x continuous at x equals 2? Kelly Bach. What are we supposed to look for? Okay, that's perfect. So if I'm not like trying to prove it or write everything out, that's a good way of saying it. You're basically just going to plug 2 into both of them to figure out if they're the same. You're trying to figure out if they meet up or match up. Yep, that's a good way of saying it. If we're trying to write it calc ways, or like calcy, we would say the limit of f of x to the left of 2. We would say what is f of 2, and then we would say what is the limit as x approaches 2 from the right, which is exactly what you had just said, essentially. So to the left of 2, I'm going to pick the top one. Left of 2 and at 2. The bottom one is to the right of 2. And that's because it was less than or equal to. The bottom one is greater than. The less than and the greater than symbols are what determine which one is from the left, from the right. So 2 minus would be to the left. So I would plug it in to 1/2 times 2 plus 1, so that gives me 2. F of 2. I'm actually still going to plug it into the top equation because it's less than or equal to. So it's still 1/2 times 2 plus 1. Still 2. And then 2 plus, I'm going to plug it into 3 minus x, because that's x is greater than 2, which gives me an answer of 1. Lucas, I don't think you answered yet today. Could be totally wrong. I might have already forgot. Did I call on you yet? No, that's all right. I want to rotate through. Oh, Melanie. I haven't called on Melanie. Melanie, is this one continuous at x equals 2? And or do you want me to guide you? Oh, it popped up. I can't see it. I can't move it because my recording's in the way. Can you just tell some? If your mic's not working, just tell somebody else what to say. Okay, perfect. And the answer is no, because all 3 of these are not the same. The only way your answer is going to be yes is if all 3 are exactly the same answer. So no, not continuous. And just out of curiosity, let's see, Caden Luden, what kind of discontinuity would this have? Maybe his mic's not working either. Jackson? Jackson, what kind of discontinuity would this have? Okay. Do you remember the difference? I was going to say you should have written it down like 5 minutes, or not 5 minutes ago. Who am I kidding? 15 minutes ago. Perfect. There's a gap or a space between these two. So this would be a non-removable discontinuity. At x equals 2. I mean, part of the annoying thing is this, is they can ask just about any kind of question. The questions get varied a lot. You're given all the same information all the time, but the questions vary quite a bit. Do you guys want me to give you a different one that's kind of like weird and has parts to it that I know have confused people in the past? Well, I will. All right, sounds good. Nobody, maybe you answered, maybe not. Now I got to try to come up with one that works in my head. Okay, so this is going to be a piece function. Wait, no, I don't want to ask, is this continuous? Identify any discontinuities. That'll be easier to phrase. So when it says that, that means if there are discontinuities, then you should say if they are removable or non-removable. Take a couple minutes. You can even work with people around you, try to figure things out. I'll put some Jack Johnson back on in the background. It's like Jeopardy music. I've got the soundtrack for Curious George. I'm kind of weird. I really like it. Well, let's see, who was the answer to? Haley, maybe? Haley, did you answer yet today? I'm not asking you to answer right now. Just perfect. Then I'll let you be the spokesman for the entire class whenever you get done. Oh, shoot. I forgot these are going on YouTube. I hope putting the music on in the background doesn't, make me take the video off. How we doing, Haley? Are you, if you're stuck on part of it, that's okay. We can kind of work through it together, too. Okay? We need a different color. We need like Vikings purple. We got a cool purple color here. I don't know if you can see this. That's kind of dark. All right, that works. There, now we got a Vikings theme. Because they had their most successful weekend this last weekend when they did not play. All right, give me one of them, Haley. Okay, how come we're calling them holes? That's very true. So those would be undefined values. A hole is only specifically when a factor cancels from top and bottom. So these are both vertical asymptotes. But do you remember what they're called for discontinuities? Okay, so a vertical asymptote would be a non-removable discontinuity. So this one has a non-removable discontinuity at x equals 4 and x equals negative 2. Now, I was thinking about being really mean and switching these two around. And I say really mean because if I switch these two around, both of these, the vertical asymptotes, would not be in their own section. This one only has a vertical asymptote because x equals 4 is in the section greater than 0. And then this one only has an asymptote because x equals negative 2 is in the section less than or equal to 0. If these two zones were flipped, then this would actually be continuous everywhere. Because, yeah, in that section, yep. At x equals 0, it's continuous. It's continuous because if I plug 0 into both of them, they both equal negative 1/2. So because both sides are coming together at the same height, it's continuous at x equals 0, but they both had a vertical asymptote in their respective sections. So those were both non-removable. So very good if you guys got that. I will tell you this is a horrible, horrible trick that this is the exact style of trickiness that the AP test likes to do. They would have switched these around so that you had to make sure to know which section it was in and where and all this kind of stuff. But honestly, if you got this one right on your own, like all of it, that's awesome. That's as hard as it'll get for now. That's good. Okay, I'll be done. It's already 11 o'clock. We have 15 minutes left. If you guys, I'll leave Google Meet down or whatever, but you guys can hop off and work on your homework for the last 15 minutes, and I'll stay on here for questions if you have any. And then Caden, let's see, wait, let me pause. Let me stop the recording.